Hello everyone, this presentation is about system design and development of friction-resistive welding of polymeric material. Friction-resistive welding is based on frictional heat between the rotating tool and the base material under an axial force. And this frictional heat, along with axial force, steer the material and force them together. We focus on the main parameters that affect the weld quality, which is the welding tool, which is the most important and crucial factor for friction-resistive welding process. Then the actual force, which is responsible for forging the material together, as well as of heat generation, and the welding temperature, which is outcome of the tool design and process parameter. And after all this information, we can optimize the process. This slide shows welding tool design development, and as you can see in this slide, the conventional tool is not suitable for welding polymeric material. A stationary shoulder is essential for good service quality as well as forging effect that forge the material inside the steering zone. Different material was tested as a stationary shoulder, and at the end high performing thermoplastics had the best surface quality compared to the metallic partners. The main feature of this developed tool was the capacity of welding polymeric material without the use of additional heat source. Instead, we use a copper sleeve around the rotating probe in order to generate frictional heat between the copper sleeve and rotating tool. Two different configurations were tested during this study: lap joint of dissimilar material, which involve polyethylene and polypropylene, and butt joint of similar material, which is 3 mm polyethylene. In the first study, the main focus was tool development and process optimization. Then study a static and fatigue analysis of the produced joint and compared with the available joining technique. The second phase of this study was the butt joint of similar, and with our experience from the first case, we could improve our tool design and optimize the parameter and study other active behavior such as forces and welding temperature during the welding process. A clamping device equipped with load cells was designed and developed in order to monitor the active forces during the welding: FAX, FAY, and FZ. 4 load cells was dedicated for each axis in order to study the effect of the welding parameter on the active forces during the welding. As it shows here, different stage of the welding is clear just by looking at the graph. The first stage is plunging, then dwell time, then welding process, and the tool retraction. However, it was concluded that traverse and rotational speed have the main effect on the traversing and lateral forces during the welding. In some cases, it was possible to distinguish some defects during the welding by abnormality of the measured actual force, as you can see in the right picture. Using the stationary shoulder, it was possible to use the actual force as a welding parameter, as the actual force is almost constant during the welding. As an example, the comparison between a stationary shoulder tool and rotatory shoulder tool regarding the actual force is shown. This is our final setup for welding polymeric material. As you can see at A, this is the 3-axis CNC machine, which the tool is assembled into the spindle B, and the parent material is fixed on the synthesized clamping device, and data acquisition system at D, and also we use a thermographic camera in order to measure the surface temperature during the welding, and also the tool temperature with thermocouple shaft inside the welding tool. First case, which is lap joint of dissimilar polymer, we conducted a design of experiment using Taguchi statistical method, and mainly we focused on the welding tool design parameters in order to understand better the effect of the tool design on the weld quality. This graph shows the comparison between the optimized welding parameter and the parent material. The optimized welded specimen, as it can be seen in this graph, had efficiency of 76% compared to the highest performing parent material, which is polypropylene. However, the main and the most effective welding parameter were all related to the tool design, then rotational speed and welding speed. To compare the frictionless weld specimen with other commercially available technique, ultrasonic welding was used to produce 5 specimens and compare to the frictionless welded specimen. As you can see in this graph, the average remote stress of FSW compared to ultrasonic specimen was a bit higher due to incontinuous behavior of ultrasonic welded specimen. Also, single and double riveted specimens were produced and compared to the frictionless welded specimen. As you can see in this graph, the double rivet specimen had the best result compared to FSW and single rivet due to the secondary rivet which transfer the force to the secondary joint. Also, the fatigue life of the frictionless welded specimen were compared to the single rivet and double rivet as well as polypropylene parent material. As you can see in this SNN curve graph, even though the double riveted specimen showed a better result during the tensile strength test, however, their fatigue results were almost the same as the frictionless welded specimen due to the different failure mode during the fatigue. In the second case study, 3 mm polyethylene was welded in butt joint configuration. 4 different welding parameters were chosen in 3 levels, as you can see: tool diameter, rotational speed, welding speed, and axial force. In this case, as the tool was already improved in the final tool design concept, we focused on optimization process regarding the welding parameters than the tool design. Also, 3 different temperature measurement technique was used during this welding: thermocouple on bottom of the plates, and also measuring the surface temperature with thermographic camera, as well as the tool temperature using thermocouples inside the sleeve. The L9 Taguchi design of experiments was used to optimize the process, and as you can see here, the measured temperature as well. However, the best result achieved when the weld temperature was higher than the melting point of the parent material, which states that friction stir welding of the polymers is not solid state as a metallic material, and in order to achieve quality welds, we need to exceed the welding temperature. And the optimized welding parameter in this case using this tool is the 5 mm probe with 2500 rotational speed, 70 mm per minute welding speed, and 950 Newton for axial force. Also, you can see in this picture how the temperature affects the weld quality. Just by increasing the rotational speed along the weld bit, you can see the improvement on the surface quality and weld strength due to the sleeve effect, which refers to the boundary that the sleeve creates above the parent material. And for the conclusion, as stated before, welding tool is the most important factor affecting weld quality and appearance in this process. And probe should have grooves or thread in order to steer the material from advancing style to the retrieving style. The use of high-performing thermoplastic for stationary shoulders such as PIC creates very good welds with the excellent surface quality. Also, LC size and geometry have a strong effect on the welding temperature. And with an appropriate tool design, no external heat source is needed. Regarding the axial force, it is responsible for forging pressure and heat generation during the welding. The developed device enabled to use the axial force as a welding parameter, and the welding speed and the rotational speed has the main effect on the traversing and lateral forces during the welding. Also, the developed synthesized clamping device can be used for health monitoring of the welding process. The applied force is kept constant during the operation using a stationary shoulder tool, which helps us to use the actual force as a welding parameter even using a position control welding method. Parameter optimization is a crucial factor to obtain the optimum weld temperature. The final tool design was able to generate up to 400 degrees heat uh, and consequently increasing the welding speed up to 10 times. Also, dwell time is responsible for heating the tool before advancing, and the weld temperature can be controlled with rotational speed and welding speed and axial force. In general, good static and fatigue behavior were found for polymeric material, and with using the final tool design and the process optimization process, we could achieve 97 strength of ultimate tensile strength of the welded specimen compared to the. Thank you for your attention.